In the previous session, we have discussed about the state models, and we haven't solved it, and we have identified the input output variables and the input variables include this manipulated variable and the disturbance. Now you see, for this simple storage tank model of storage tank, we have got the final model equation as A dH dt equal to Fi minus F, where this F, where let F is equal to beta root H, which we have established from Bernoulli's equation, applying Bernoulli's equation between the liquid surface in the tank and the outlet of this effluent line. So, the resulting equation becomes this. So, obviously H is the output or the control objective or the state model, right. Fi is the input and beta is the manipulated variable. So, here we have to note that this is a nonlinear term. And overall it is a nonlinear equation. So, we cannot solve the equation analytically. Definitely the numerical solution, the scopes of the numerical solution remains intact, but we cannot solve it analytically. So, for a first of its kind understanding about the input output model, right, and additionally the dynamic response of the system, we have to go for analytical solution, and it's always theoretically it is always favorable that we have an analytical solution and we can predict the trend without actually going for numerical evaluation. So, if I have to do that, we have to convert this entire equation into a linear equation upon linearizing the term. So, our task here is linearization. So, we will not work with that specific equation in particular, we will again come back to that equation, but let us go for a general description of a state model as dx dt is equal to fx, where fx is nonlinear. A nonlinear function of x, right. So, in general you see this may have a trend fx versus x like this. So, now we have to solve this equation and we cannot do it unless we convert the equation into a linear form. And the point here that we are not bothered about this dx dt, we are actually have to focus on this fx. So, fx we have to linearize. And the theoretical toolbox what we have to use here, or the mathematical tool, is a Taylor series expansion, right. So, you see that Taylor series what it states? Taylor series states that fx can be expanded about any base point xs or x0, let us say x0 plus we have x minus x0 into f prime x at x0 plus higher order terms, right. So, in this form if I neglect the higher order term, considering this x minus x0 is pretty small, we can truncate that series after the first derivative term and we can approximate it as fx0 plus x minus x0 into f prime x at x0. So, definitely there will be an error, right. So, error which is defined as fx minus fx naught plus x minus x naught into f prime at x naught is definitely not equal to 0, and epsilon increases as x minus x naught increases. So, we have to consider a neighborhood, or we have to restrict this linearization process over the neighborhood domain of x naught. Just like, for example, geometrically what we are doing, say if this is the point x naught, we are approximating the curve by means of a tangent drawn at the same point. So, if I limit myself over here, that is x naught plus delta, where delta is a very small number, and x naught minus delta, the error, this is the measure of that error, right. This is the error, and here at this terminal point, this is the error. So, you see that error progressively increases as we move far away from x naught. So, if I have to go for approximate solution of this equation, which is what kind of engineering working equation with desired level of engineering accuracy. So, we have to restrict ourselves over this domain. If we go beyond this, now what is the value of delta? Definitely it is a point of debate. So, that depends on the type of the system, nature of the curve, etc., etc. But theoretically we can understand that we have to be close to that point x naught, because as we move away from the point base point x naught, the error of replacing this fx by its respective Taylor series expansion progressively increases. So, we will replace this fx by the Taylor series expression truncated after the first term. So, linearized equation becomes dx dt is equal to fx naught, we will write it as fx naught minus x plus x minus x naught into f prime at x naught. Now, the point here, that here if we just for example, if we consider that previous term beta into under root of h, so it will be beta into under root of h naught plus beta divided by 2 under root of h naught into h minus h naught. So, my system equation becomes dh dt is equal to fi minus beta into under root of h naught minus beta divided by 2 under root h naught into h minus h naught. Okay. So, with that equation we can proceed for the solution, but before we go for the actual solution, we have to answer a question. That what is that question? What is the best selection for the base point, that is x naught in general, right. So, you see that if I think now from this real life perspective of the storage tank, so there must be a set point for every system, every control objective, which is most important, every control objective, there exists a set point, right. And if it is fitted with a controller, which actually is our objective, that we have to design a controller with appropriate parameters such that the h is always even if it deviates from this set point, it will be close to that set point, right. So, our random dynamics of this H versus T may be like this. This is H naught, this is T naught, T equal to 0. So, the dynamics may be like this. Like here, previously at before time t equal to 0 or t less than 0, it was at H naught. That means it was at the set point. Now, because of some disturbance, maybe a change in Fi or increase in Fi, it shoots up. But immediately as it shoots up from the set point, the controller gets activated. It will increase the value of f upon tuning the beta. So, it will again start decreasing, but definitely there will be an inertia in the dynamics of that system. So, it will go down below this H naught, and finally after 2 or 3 oscillations it may settle down again to H naught, and it will adjust itself, the system will adjust itself with the increased increased Fi, right. So, because of that increased Fi, beta will be tuned such that f also changes or increases, and finally again H will be brought back to H naught or Hs rather. This is not H naught, this is Hs, the steady state or the set point. Okay. So, as the state variable in a control device always be in the neighborhood of the corresponding steady state value we consider Xs to be the best selection for the base point of linearization of Taylor series expansion. Right. So, we use this steady state to be our base point for Taylor series expansion and the respective linearization. So, with x is equal to xs, we have dx dt, see dx dt is equal to fxs plus x minus xs into f prime of xs. Right. Now, we can directly use this equation and go for the solution, but see, we are actually more focused, instead of this absolute value of the variable, we are more focused on the respective error, right, or its deviation from the set point values. Like instead of what is the value of h, when we are going for a general analysis, we are more interested here instead of the absolute value of h. So, we restructure the equation in terms of its deviation variable, its deviation from the respective set point. Accordingly, we define the so-called deviation variable. So you see what is deviation variable? X prime is xt minus xs. So this is the deviation variable. So once we have defined the deviation variable, we have to write the equation in terms of the deviation variable. So let's say this is equation A. The respective steady state equation is dxs dt, which is definitely 0 because it is at steady state, and that must be equal to fxs plus 0 because at steady state x is equal to xs. So basically the equation reduces to the form fxs is equal to 0, but we are writing this dxs dt because to extract certain mathematical advantage. So this is equation B. So we subtract. So subtracting B or equation B from A, we get what we obtain, ddt of x minus xs is equal to x minus xs into f prime of xs, and that is dx prime dt is equal to f prime t into f prime, or rather as we have to change this, so let's not write this f prime because otherwise it will be confusing. So df dx at xs, so here it is x prime into df dx at xs. Right. So this equation is much simplified compared to equation A. Now you see, and also there is an advantage that we have generalized the initial condition. Here what will be the initial condition? At x is equal, or at t equal to 0, at t equal to 0, x is equal to xs. And here at t equal to 0, x prime is equal to 0 everywhere because x prime initially the system is at its set point. Okay? So with that understanding, if I now look for a specific equation like whatever we have initially cited, this equation, what will be the respective form of that equation, linearized equation in terms of its deviation variable? So let's solve it out. So a dh dt is equal to fi minus beta into root hs minus beta divided by under root 2 hs into h minus hs. So here a dhs dt is equal to fi comma s minus beta root hs minus 0. So this is the steady state equation. So if I subtract, it will be dh prime dt is equal to fi prime minus beta by root 2 hs into h prime. So here you see what will be the initial condition at t is equal to 0, h prime is equal to 0. So that's universal. That's universal condition and universal initial condition, and with that we can solve this equation because it is a linear one. And it's typically linear equation. You shift this to this h prime term on this side and go for this Leibniz formulation and can solve the linear differential equation. I am not going into that. Now, if I have a multivariable system, right, multiple state variables with many manipulated variables and the manipulated variable and these disturbances, right. Here you see that actually there is a point. Point is that though we have linearized the system, but we haven't considered that exact linearization. Why? Because beta is also a manipulated variable, and that is why it is an input variable. It is a linearization with respect to the state variable whatever is given in every book. So, if I think of dx dt, let us say it is dx dt is equal to x1, x2, xn, then m1, m2, mm and d1, d2, dn. So, actually dx dt here, just like here, that dh dt is a function of input, right, the state variable itself and a manipulated variable beta. So, the general structure in the handout, see in the handout I have only considered this, but truly in this sort of differential equation dx let us say I, dxi, and here it is fi, right. Truly this is the form, and I is equal to 1 to n, right. So, there will be state variables, there will be manipulated variables, and there will be disturbances, and we have to linearize. This function is nonlinear, we have to linearize the term. So, we will go for multivariable Taylor series expansion. So, what it would be? That we can write dx1 dt is equal to f1 x bar 0 or x bar s, m bar s comma d bar s, plus where this x bar is equal to x1, x2, xn transpose, m bar is equal to m1, m2, mn, mm transpose, and d bar, or let us say it is dk. D bar is equal to d1, d2, dk transpose. So, first it is the function at its base point. Next, it will be del f1 del x1 s means at steady state into x1 prime plus del f this 1 del xn s xn prime plus del f1 del m1 s into m1 prime, then del f1 del m s into mm prime plus del f1 del d1 s into d1 prime, and finally del f1 del dk s into dk prime. So, that is the basic expansion, and similarly we can write that dxn dt is again fn x bar s, m bar s, d bar s plus all these terms, but the derivative with respect to, or it will be del dfn, or the same expression, only f1 will be replaced by fn. So, if I write the steady state equation, steady state equation will be dx1 s dt, which is 0, is equal to f1 x bar s d bar s, or rather this m bar s and d bar s, and the xn s dt, which is also 0, is equal to fn x bar s, m bar s and d bar s. So, if I subtract the steady state equation from this original equation, upon subtraction dx1 prime dt is this del f1 del x1 is x1 prime, del f1 del xn is xn prime, del f1 del m1 is m1 prime, plus del f1 del mm is mm prime, del f1 del d1 is d1 prime, plus del f1 del dk is dk prime. And similarly, we can get that dxn prime dt is equal to del fn del x1 is x1 prime, and finally going to del fn del dk is dk prime. So, if we can rearrange this, we can rearrange in the form of a standard matrix expression, and we can write that dx1 prime dt and dxn prime dt typically it will be this del f1 del xn del x1 x into del f1 del xn is into del f1 del f1 is del f1 del mm is del f1 del d1 is del f1 del dk is right, and finally del fn del x1 is del fn del xn is del fn del m1 is del fn del mm is del fn del d1 is, and finally del fn del dk is, and it should be multiplied by ঠিক আছে x1 prime, x2 prime, xn prime, d1 prime to m1 prime to mm prime and d1 prime to dk prime. So that is the linearized state model representation of that system. So, just for example, we can think of example of star tank heater. So, dH dt is equal to Fi by A minus beta into root H by A, right, and dt dt is equal to Fi so dt dt will be Fi divided by A into H into Ti minus T plus U into At into this T steam minus T divided by rho Cp. So if I go for this, so this is basically f1 x1 to xn, or f1 of this this ht, then manipulated variable are beta u, then disturbances, that is fi ti, right, and this entirely it's f2 ht beta u fi ti, right. So we can write that dh prime dt into then dt prime dt so derivative of this f1 with respect to h. So this derivative fi, this is 0, and this derivative is minus of beta by a into 2 into under root h's. That's the derivative of entire function with respect to h. Derivative with respect to t is 0. Derivative with respect to beta is minus of hs by a. Right? Derivative of u is 0. Derivative of with respect to fi is 1 by a. Derivative with respect to ti is also 0. And for the second, this derivative with respect to h is this minus of fi s divided by a into hs square into tis minus ts, right, and there is no other h. Now derivative with respect to t, so this is the first term here. So derivative with respect to t, here the term will be fis by a hs into minus 1, right, plus u into at divided by rho Cp again into minus 1. So that's the derivative us here. So everything is evaluated at steady state. Now derivative with respect to beta, that's 0. Derivative with respect to u, which is here it will be at into tst minus ts divided by rho Cp. Okay. Derivative with respect to fi. So derivative with respect to fi will be tis minus ts divided by a into hs, and derivative with respect to ti, definitely it is here. So it is fis divided by a into hs, and that should be entirely multiplied by, in the same sequence of the variable, that is h prime into then t prime, beta prime, u prime, fi prime, ti prime. Okay. So that's the linearized state model of that system. Now once we are done with this linearization, so finally our target with which we have started the mathematical model, finally our target is to derive the input-output model, right. So from the state model we have to generate the input-output model, and input-output model is nothing but the solution of the linear or linearized state model. So already we have linearized it, so now we can solve it. So let's consider the example of starred tank heater with an additional constraint of constant level. This is an additional constraint, right? And that actually simplifies this equation. So, H is constant. So, first equation becomes null and void. The second equation, so the only state equation, we have dt dt equal to Fi by V Ti minus T, right, plus U into At divided by rho Cp into Tst minus T. So, Fi is also constant because H is constant, right, because this Fi, dH dt is Fi minus F divided by A. So, if H is constant, Fi is equal to F is equal to the respective steady state values. So, dt dt we can write 1 by tau. Here the tau is the space time of the reactor under this constant level condition. So, Ti minus T plus UAT divided by rho Cp Tst minus T. So, tau is basically Fi minus F. Now, you see actually this is also nonlinear because U is the manipulated variable and T is the state variable and they are in the product form, right. But hypothetically, let us not go for linearization, right. Hypothetically, we consider Tst to be the manipulated variable. So, if Tst is manipulated variable, next definitely the equation is linear because U then is a constant. So, we don't want to go again into linearization and make this equation structure complex, because actually our objective is not to solve this equation for this input output model. Rather we want something else, rather it is a kind of demonstrative example that how to solve the input output model from a given state model. So, we bypass the tedious task of linearization, though already we have done it here, right. This is a typical example given in the book of Stephanopoulos. So, let us follow it in toto. So, here if this is the case, so if further write dt dt equal to 1 by tau Ti minus T, now everything is lumped into a constant k, that U is no longer a manipulated variable because hypothetically we have considered this Tst to be the manipulated variable. So, k into Tst minus T. So, further this is dt dt plus this 1 by tau plus k whole bracket T equal to 1 by tau Ti plus k Tst. And this 1 by tau plus k, we consider it to be alpha. Right. So, that is my final state equation, but we have to further convert it into deviation variable form before we solve for this input output model. So, steady state equation is dTs dt 0 plus alpha Ts is equal to 1 by tau Ti comma s plus k Tst comma s. So, if I subtract these two equations, this and this, from this equation, I will get dt prime dt plus alpha t prime 1 by tau ti prime plus k tst prime. Right. And at t equal to 0, now the this initial condition is also universal, ti prime equal to tst prime, all are 0. So next we have to solve this equation, and it's a typical this Leibniz linear differential equation. So my integrating factor is e to the power alpha t. So we write that ddt of t prime into e to the power alpha t is equal to this 1 by tau ti prime plus k tst prime whole bracket into e to the power alpha t. So t prime into e to the power alpha t minus 0 is 0 to t 1 by tau ti prime plus k tst prime into e to the power alpha t dt. And essentially this t prime t becomes e to the power minus alpha t 0 to t 1 by tau plus k 1 by tau into ti prime plus k tst prime into e to the power alpha t dt. So that's my input output model. So that's the typical input output model, and if you go for a schematic, so this is the input output model. And schematic of Io model, that's typically this ti prime t will be the input, there will be multiplier block 1 by tau, then tst prime, another input, another multiplier block k. Next these two signals are to be added, going to a mathematical operation block, that e to the power minus alpha t 0 to t, this into e to the power alpha t dt, and it produces the output t prime t. So that's my input output model. So what we note here, that even for a very simple system, the input output model is not so simple, that here we have a complicated mathematical function, right, that we have to accumulate that signal after multiplication, go on adding and go on integrating it. Maybe we have to use the Simpson 1/3 or this trapezoidal rule, and every time we have to multiply it by e to the power minus alpha t, and then we can produce the output. So overall this block and the respective representation is not so easy. And on the other hand, here it is a first order differential equation. Think of a second or third or nth order differential equation, which is always probable. That if I have a second order differential equation, the entire equation and the respective schematic will be intractably complicated. So that's why, because what is the source of this complexity? Because my state model is a differential equation. Okay. So our conclusion from this input output model, whatever we have derived, is that inference about the input output model is that even for a simple system, the Io model is appreciably complicated. Right. And that's the general conclusion. It's not a particular one, because we have this complex mathematical function to be performed. The root cause of this complexity, is that the state equation is either a state equation is in general a differential equation. So we have to get rid of this differential equation, right? So what we will do? So remedy or alternative. Alternative approach, that is, change the domain, change the independent variables domain from time to something else, such that it becomes an algebraic equation which is much easier to solve. And for that, we actually invoke this Laplace transform, right? So Laplace transform, it changes the domain from time to this Laplace parameter or Laplace variable S. And we know that every differential equation, we have seen it in engineering mathematics, that every differential equation actually changes, ODE changes to an algebraic equation in Laplace domain, right? So we have already discussed the detail, these rules and transformation relations for Laplace and inverse Laplace transform, and we have seen that how we can convert the linear differential equation, ODE specifically, to an algebraic equation upon taking the Laplace domain. So just for the most important transformation relation is Laplace transform of a derivative. So this is the most important relation we are going to use here, because all we have are the linear differential equation. So again, if we think that the example of constant level star tank heater. So it is basically the dt plus alpha t, or rather indirectly deviation variable, 1 by tau ti prime plus k tst prime. So upon or by Laplace transform, so we have s into t prime bar s minus t prime in time 0 plus alpha t prime bar s is equal to 1 by tau ti prime bar s plus k tst prime bar s. Right. Now you see here we will have another advantage of transforming the equation in deviation variable. This term is 0, right, because it's a deviation variable evaluated at time t equal to 0, so essentially this term reduces to 0. So because it is 0, see, because it's 0, the equations, the overall form of this equation gets simplified to some extent. So we can write that t prime bar s is equal to 1 by tau s plus alpha into ti prime bar s plus k divided by s plus alpha tst prime bar s, right? And that becomes my input output model in the Laplace domain, which is much more simplified compared to the previous one. And Laplace domain is a standardized transformation, or Laplace transform is a standardized transform. So instead of time domain, if we switch to Laplace domain, it's pretty simple, and we can write, see, that here we have ti prime bar s, then we have here 1 by tau s plus alpha, and tst prime bar s, it is k divided by s plus alpha. So these two Laplace domain transform signals are added to generate the output in Laplace domain. So this is the typical input output model, schematic Io model in Laplace domain, which is much more simple. So we have to understand that we will now go for writing or developing the input output model, or finally developing the input output model in Laplace domain. So let's have some generalized example of where we are having the single input, single output, and they are related, like general examples of mathematical model. Seesaw systems. That is single input, single output system. Right. In time domain schematic, it is just like this. This is the system. Here we have deviation variable of the input producing deviation variable of the output. And let the linear or linearized state model be an we are going for a general format of nth order, this linear or linearized differential equation, right? An initial condition at t equal to 0, dy prime dt, d square y prime dt square, dn minus 1 y prime dt to the power n minus 1, they are all 0, right? You may be thinking that how come it is possible, and what is the basis that we may be going for a kind of simplification such that definitely y prime is 0, but derivatives can never be 0, no matter whether we are writing it in deviation variable or not. But we are assuming that, okay, for this system the initial all the derivative vanishes. Okay. So actually the thing is that we will see that this is true. This is true for any higher order system. So order means the order of the system means the order, we will see later, that order of the differential equation which represents the state model of the system. Like this is a system of nth order, right. So we will see that for third order system the second and first derivative terms for all third order system will be 0. For a second order system the first derivative is also 0 at t equal to 0. So that is a general physical understanding regarding the structure of that state model and the initial condition. So this is physically also true, we will see through the examples. So considering this, all the first and higher order derivatives are equal to 0, Laplace transform will result an s to the power n into y bar s, because and the rest of the terms like as predicted here are all zeros, plus a n minus 1 s to the power n minus 1 y bar s, plus finally a naught y bar s is equal to b into f bar s. So y prime bar s divided by f prime bar s, which we call the transfer function of that system. This is s, right. So this is transfer function of the system, and that is equal to b divided by a n s to the power n a n minus 1 s to the power n minus 1 plus a 0. So transfer function by definition it is equal to what? The Laplace transformed deviation, a Laplace transform of output's deviation variable that divided by Laplace transform of inputs deviation variable. Provided all the other inputs, if any, are kept at their respective steady states, right. Like we will see what is the implication of the statement that all the other inputs at their respective steady states. So we can understand the implication of this definition of this transfer function once we go for these multiple input systems, right. So second example, the second example is MISO, multiple input single output system. Now what I have missed here, a representation which is pretty elementary, but the input output model, how will you represent? We will go for a block in which the respective transfer function will be inscribed, and we will show the input and output in Laplace domain, and this is called the block diagram of the system. Right. This is a typical block diagram. You just construct a block, inscribe the respective transfer function, and input outputs Laplace this Laplace transformed in terms of the deviation variable. Just you simply represent it, and that became the block diagram of the system. So, multiple input, single output system. See, the time domain schematic is this: f1 prime t, f2 prime t, and finally m prime t, producing only a single output, that is y prime t, and the relation is just the same. This is the respective final form of the state equation, which may be originally linear, or in most of the cases it is linearized. Right. So, if I take the Laplace, and again we consider, or we for the time being tentatively consider that at t equal to 0, dy prime dt to dn minus 1 y prime dt to the power n minus 1, they are all 0. So, if I take the Laplace transform of this entire equation, I will get a n s to the power n plus a n minus 1 s to the power n minus 1 plus a 0 whole bracket y prime bar s is equal to b1 f1 prime bar s up to bm fm prime bar s. So, essentially we have y prime bar s is equal to b1 divided by a n s to the power n plus a 0 into f1 prime s plus bm divided by a 0 s to the power n, sorry, a n s to the power n a 0 into fm prime bar s. And finally, we can write it as y prime bar s is equal to g1 s f1 prime bar s g2 s f2 prime bar s and gm s fm prime bar s. So, you see here we can understand the implication of the last part of the statement, that all the other input, if any, we are keeping at their respective steady state. So, if I am thinking of the definition of G1, right. So, we are keeping all the other forms of input at their respective steady state. So, F2 prime, F3 prime up to Fm prime are all 0. So, this part vanishes and we get G1 as a transfer function of F1 connecting Y, right. So, the respective block diagram is F1 prime bar S, here we have G1S, and similarly Fm prime bar S, where it is GMS. So, there is an adder, right, and finally producing the output y prime bar s. So, that is the input output model of the multiple input single output system. So, next is the last example. MIMO, multiple input, multiple output, right. multiple input, multiple output. So we have here this. Now let us not go for this nth order equation, it is pretty simple, we will explain it. Let us think that this is a typical first order equation or first order system where dy prime dt plus a11 y1 a12 y2 prime b11 f1 prime plus b12 f2 prime and dy2 prime dt plus a21 y1 prime a22 y2 prime b21 f1 prime b22 f2 prime. Right. So if I take the Laplace, so S plus a11 y1 prime bar, a12 y2 prime bar, b11 f1 prime bar, b12 f2 prime bar, and here a21 y1 prime bar plus S plus a22 whole bracket y2 prime bar, b21 f1 prime bar, b22 f2 prime bar. So definitely these two are simultaneous algebraic equations with two variables y1 prime and y2 prime as output and two input variables f1 prime and f2 prime bar in Laplace domain basically. So you see that if we solve, we can get a structure like y1 prime bar s is equal to g11 s into f1 prime bar s plus g12 s into f2 prime bar s and y2 prime bar s is equal to g21 s into f1 prime bar s plus g22 s into f2 prime bar s. Right. So the respective this definitely g1 prime, g11, g12, g21, g22 we can solve and get. That's not important because we are doing or discussing a general structure, right. So you see we can write it further as y1 prime, y2 prime bar is equal to g11s, g12s, g21s, g22s whole bracket f1 prime bar s, f2 prime bar s. So this is called the transfer function matrix. And order of the transfer function matrix, see the number of column must match with the number of input, whereas the number of rows must match with the number of output. So order of the transfer function matrix is the number of rows, right? Output multiplied by number of input, right. So here it is 2 cross 2 because we have considered 2 input 2 output system, but if we think of 3 outputs, 3 inputs and 2 outputs, right, it will be a 2 cross 3 matrix. And the respective block diagram, you see So F1 prime bar S, it's going to G11 S and this G21 S, right, and F2 prime bar S going to this G22S and G22S and G12S. Now from G11 and G12 we are getting Y1. And from here so this is a typical block diagram of that input output model. Now you see, just in a real life example of chemical process industry, we can think that okay, it's an absorption column, right. So here we have GS Y, let's say it is 1, and this is GS Y2, LS X2 and LS X1. Okay. Now GS and LS are nearly invariant, whereas okay, then it creates a problem. Okay, let's say GS and X2 are invariant, whereas Y1 is the disturbance and LS be the manipulated variable, Y2 and X1 are outputs, right. So with that we can think of if we can properly model. I am not going into the model part, right. We can write what are the output Y2 and X1. So Y2 prime S, X1 prime S. So you can write this G1S or G11S, G12S, G21S, G22S, whole bracket into Y1 prime bar into LS prime bar, right. So this gives you the input output model of the system, and with that we can actually design the controller. Okay. So in the next session, so that's all about the general discussion of the process control. In the next session we are going to start the discussion about the first order system.